All right, so we are actually today starting a new lecture. And I don't know that we're actually going to get the computer part of it today, so I think it's mostly going to be just lecture. And that is about unavoidable errors in computing. So far, you've done plenty of avoidable errors in computing. We call all those bugs. But basically, that's when you put in a typo in there, you don't indent the way you're supposed to indent, and you get an error because the computer is not executing what you wanted, or what you intended it to execute. So those are ones that you can actually remove, and once you remove them, it's going to execute what it can. However, some of these errors we actually cannot avoid. Okay? So there could be, again, we refer to all kinds of errors, bugs, and the process of fixing them, debugging. So there's best practices, and that is really just, as you write the code, test small pieces of it at the same time. And often it's like creating a very small problem, something that you can manually compute and check that your computer is doing the same. And we've done plenty of that in homework. If you noticed, I asked you to either do things by hand and things by computer so you can compare the two. That is basically a way to weed out bugs. Now, there are some errors that cannot be avoided. And one of the most common ones is truncation error. So when I have a mathematical formula that I'm trying to compute, like this sum that goes from 1 to 1,000, 1 to infinity, that you do a lot of these, which calculus, or 7 or D, or I'm constantly missing C's and D's in math courses in the sequence. So essentially, you have this infinity sum. Okay? It's infinity. We can't reach infinity by definition, so we gotta stop somewhere. Okay? And good news is that often for as much as we can measure error, it's actually just fine to go to 1,000. You don't need to go to infinity. Okay? You're going to get accurate enough, okay, for all of the intensive purposes. So good news is that we don't have to go to infinity, but there is an error nevertheless between what we actually compute and what mathematical formula is demanding to compute. And the difference between the two is called truncation error. So we basically approximate mathematical formula with some sort of finite sum. The second error is the round-off error. So that's basically when we are trying to it's based on the fact that my number, like pi, that we were trying to approximate last time, okay, it has infinite number of digits in decimal system. Okay? So if I were trying to store it in computer memory, well, I have finite memory to store it. And not only that, I also have to translate it from digital world to binary world that operates only with zeros and ones. So it doesn't have 10 digits, it actually has 2. And we're going to go through the process of translating between the two, just so that you get the idea of how computers actually store numbers. Okay? And in that process, we cannot, often it's not even like I can actually store a number per se, but if I have two numbers that are very different, like 1,000, and this is 10 to the minus 8 or 9, okay? Then two of them are so far apart that it's extremely hard to store the result of that calculation into the same finite spot of memory. So we will actually have some round-off error in the process. So for all of effective purposes, this ends up being just 1,000. Okay? So those are round-off errors that are related to storage of numbers in the computer. Yes?
But when you multiply, it's going to work a lot better, right?
Yes. So, well, again, because the result of the multiplication is the number that is closer. Right? So, essentially, why that is, and we're going to get to the representation, is because I use scientific notation of a number. So this is 1 times 10 to the 3, and this is 1 times 10 to the minus 10. I didn't count them. That's a minus 10. And when I'm adding them up, I have to represent that number in scientific notation as well. However, that number is, because 3 and minus 10 are so far apart, I have to bring them to a common and represent them again as something times 10 to the something. Okay? And in the process of doing that, it's going to be 1.00001 times 10 to the 3. And it's this 1.0001 that I'll have trouble storing precisely. Because I have finite space to store that first part and exponents. So we store exponents and the actual piece that goes inside. So that's why. So when I'm translating them back and fitting that into one box that has that specific. So I have no trouble storing 1,000. I have no trouble storing this, because they're 1 times 10 to the something, and I have space for all that. But when I add them up, it's extremely hard to find a nice 1 times something representation of that sum, and that's where I get chopped up. Okay. So just fitting them into the same box. Whereas when I do the multiplication, okay, then the result of that operation is 1 times 10 to the minus 7, which I have no trouble storing. That's what it comes down to. Okay. All right, well, that was a quick introduction of what we're going to get to. So first we have to measure errors, and we did that actually in our last exercise of computing p or pi. So basically, technically, I have 2 types of errors. One is absolute, the other one is relative. So absolute value, absolute error is simply the difference between true value and whatever approximation we have. That is great when we know the true value. So last time in our exercise, we pretended that whatever NumPy stores as p is our true value. It's also an approximation. Everything is approximation. Everything on a computer is an approximation of number b. But we are calling that the true value. So if I have a bridge whose true length is 100, but I measure it somehow as 99, my absolute error is 1 centimeter. If I have a river that is, I'm going to guess that this is a width of the river rather than length. The weird river that is only 1,000 centimeters long. But basically, if I make the same absolute error relatively to the size of what I'm measuring, those are 2 different things, right? So making an error of 1 centimeter when something is 1,000 centimeters long, that's a relative error of 0.1%, 0.001. Whereas when I make a 1 centimeter error with respect to something that is 100 centimeters long, then my error is 1%. So we tend to, if we're going to compare 2 different things, we should compare relative errors and not absolute errors. You can work with absolute errors only when you're kind of working with the same kind of thing. So don't compare apples and oranges using absolute error. Compare them using relative error. But again, nevertheless, we will work with what we have. And then the only other thing is that I might have a true value of whatever it is, but that true value is also often another measurement. True value is whatever is the best measurement I have. Okay? So in itself, it might be also a slight approximation, I don't know. Right? But it's the best what I have. Okay? So, or it might be some sort of analytical formula, result of some analytical formula. All right. So, again, we have truncation error, and that's something that is controlled by the user. So we're going to often figure out where to stop, and that depends on us. So that's something that in the process of working on a problem, you should kind of go and gauge what your error is, so that you're simply aware. Error in itself, or making an error, is not bad. What's bad is if that error or that amount of error hurts your problem, or you solving the problem. Okay? So you're going to always make some error, right? But you have to kind of gauge how much error you're making. So if you have a serious representation like this, and you chop it up, and so e to the 1, for instance, is 2.71 roughly, right? So if I stop at 1, I'm obviously making a pretty gross error. Okay? Then if I add 1, so I'm evaluating 1 plus 1 is 2, that's getting closer to 2.71. Then I'm going to add 1 over 2, so that's 0.5. Right? So I'm going to get to 2.5, that's getting closer to 2.71. So as I add these parts of this series, I'm going to get closer and closer to the result. And often we have to the result I want, and often we have to actually figure out, well, where is this error and how it changes as I'm adding more elements to this sum. Okay? So that is basically measuring truncation error. Another formula, so this is just when I have series representation and I'm stopping at some point and using only certain number of elements in this sum. Another common approximation is so-called derivative of a function. So often we know that we're going to approximate derivative as difference in function values divided by the difference between the points where I'm evaluating it. So if I have 2 points, xi and xi plus 1 that are close to each other, then I'm going to approximate derivative as f of xi plus 1 minus f of xi divided by xi plus 1 minus xi. So this is simply slope of the curve between 2 points, right? So that's basically whatever function you have, you find 2 points and you look at that linear segment between them. That's your approximation of the derivative at that point. Okay? And then you are making an error there, and as those 2 points get closer, this xi and xi plus 1, you get better and better, or closer to the actual value. But it's never precise. So one of the most common formulas that are approximating functions is so-called Taylor series. It's also used to analyze how accurate numerical methods are, particularly because numerical methods are often busy solving differential equations. Okay? And in differential equations, I have to replace derivative that I just showed you with that approximation to the derivative. And it's actually analyzing this Taylor series that typically tells me how large error I'm making, especially depending on the spacing between the points. So Taylor series is evaluated. So if you are wondering why are we solving so many problems related to Taylor series, that's actually why. So f of x is, this is something that I know, f of x0 is typically my starting point. So I'm evaluating function f in some neighborhood of x0. And that's f of x0 plus difference between the 2 points times the first order derivative evaluated at x is equal to x0. Plus there's this difference squared divided by, we know what factorial is? Do we remember what factorial is? Yeah. 1 times 2 here. Yeah. And then second order derivative. I can keep going, however many derivatives I actually feel like evaluating. We often go up to 2, and that's for most numerical methods, that's enough. Okay? And I know that for anything larger than that, so if I stop at some nth level here, I can go up to n, whatever n might be, then the error that I'm making is related to the derivative that is 1 higher than n. So I know that I can actually, theoretically, I could find a point on that interval between x0 and x where I evaluate this derivative and multiply by this, and I will get precisely what was left off here. So this is my error. So if I know something about the nth order derivative of this function, I have a way of gauging theoretically how much of an error I'm making. Okay? This is where a lot of applied math work goes. So when we try to derive numerical methods that work for a wide range of problems, and you can analyze them beforehand and say, well, this is what error is going to be, so you can safely use a method, and it's going to approximate things, but that's going to go well. Okay? If you always stay close to the solution, that means that your numerical method is working well. Okay. So when you figure out an algorithm that approximates a method, Okay, that's a numerical method. You have a problem and you find some sort of like an algorithm that you can write up and make computers solve it. Okay. Then the question is, are you going to get to the solution or close to the solution of the problem? The first thing that you could do, you could have a typo, you don't put that for loop correctly, then you're not going to get a correct solution. Those are avoidable errors. But then even if you type up your algorithm correctly, you're going to get only so close. And as long as you get close, we call that convergence. Okay, you're going to get to the end. The idea is that as long as you have time to wait for a computer to add all of those terms in certain sum that you do, for instance, in truncation error, as long as you have time to wait, you should get closer and closer. So that's convergence. Okay. So basically, I know that I can get, this is a mathematical way to express that I can get as close to the solution of the problem as I need to. In practice, what we do, let's say that xk is, or an xk plus 1, I'm iterating in some for loop, right? And I'm getting approximations to my solution. And at some point, my approximation to that number e will be 2.71, then it's going to be 2.711, and then it's 2.71112. So they're kind of getting closer and closer to each other. So we typically stop when our approximations kind of stop changing much. By how much they're changing, this is called delta here. So basically, I'm going to stop when they get close. And it's just the difference between the two steps that I'm making in the algorithm. Okay. All right. So let's do an exercise. Okay. Write down the formula. F of x is 1 over x plus 1. And use Taylor approximation to write down the formula for that function. So evaluate it using Taylor series. Close to x0 is equal to 1. So basically, evaluate these terms up to the second one for f of x is equal to 1 over x plus 1. And then I want you to use that Taylor series to find what is f of 2 and f of 3. No. On a piece of paper. If you really need a calculator, you don't need a calculator for these. Before we go to Python, I'd like you to do things by hand. That you can then appreciate what Python does for you as a calculator, if nothing else. And I want you to find what are the relative and absolute errors. So in this case, I know what the function is, so I actually know what the true value is. So let's see whether whatever I was talking about so far was just talk. You're all nodding. So how does my f of x look like in the neighborhood of x0 is equal to 1? The first term in Taylor series is f of 1, so that's 1 over 2. Plus, and then I have whatever x is minus 1 times, what is my df dx if f of x is 1 over x plus 1. I'm going to call that f prime. And that has to be evaluated at x is equal to x0, right? So that's for 1, that's minus 1 over 4. Plus x minus 1 squared over 2. And then second derivative for this is 2. Yes? You might remember calculus better than I do. I'm not going to count the number of years since I took it in 1996. Well, I had a version of it in grad school, so 2000, okay. Fine. Still been 19 years, okay? So times, so this evaluated at 1 is 2 over 8, which is 1 over 4. And plus whatever is left over. So this here is my Taylor series approximation to the function f in the neighborhood of 1. Works well if I'm close to 1, not so well if I get further away. Okay? So in approximating f in that neighborhood, I can then take only 1 term, 2 terms, 3 terms, I can actually keep going. And presumably, if I take 3 terms, it's going to be more accurate than just 2. So that's what I want you to confirm for f of 2 and f of 3. So did anybody calculate anything for f of 2? That's a silence right there. Okay, questions. I see a lot of people still doing this. So in this case, I know the function, right? So I can also gauge how accurate the formula is. Yes?
I was just wondering, what are we going to use for a true value?
We actually have a function. So it's true value, great question. So what is true value? Function is actually this. So true value at 2 is f of 2 is 1 over 3. Right? This is approximation to this. This is approximation to this. So I evaluate this at 2, and I evaluate this at 2, and compare the two for absolute error and relative error. The key is that sometimes actually there are methods that I can't get to this, actually. But I have these values, or I have some version of derivatives because I'm solving a differential equation. Okay? So I can get to that Taylor version of it, but I can't get to the actual value because I'm still working on it. I'm working on getting it. Right? Is everybody else following? So I got that my f of 2 approximation, it's just 1/2. If I use 2 terms, then I actually have those 2 terms, so I have 0.25, because I have 1/2 plus 1 times minus 1/4, which is 1/2 minus 1/4, so that's 1/4. Yeah. And then using 3 terms, it's 0.375. I'm trying to get to 1/3. So you can see how I'm approaching from 0.5, 0.25, 0.375. And it can go up and down, but it's as I take more terms approaching 0.33333. Yes? And it works better for a number that is closer to 1. 2 is closer to 1 than 3. If I do the same exercise for f of 3, okay, my first application, if I take just that constant, then that approximation is always the same, which is obviously not going to be very accurate. Then I actually get a 0 for f of 3 using 2 terms, and then I get 0.5, and it seems that I might be getting wobbling around and possibly never even converging. I didn't do enough terms to see whether I'm ever going to converge. So possibly this number is just the Taylor formula is not converging because 3 is too far away from 1. Okay, and function is changing too much in that neighborhood. Because my solution is actually 0.35. It might just be, well, I don't know, I didn't confirm, but it might actually, sometimes these, they get 0, 0.5, 0, 0.5, and that's not converging. Remember calculus? Yeah. Questions? Okay.
So each term in the Taylor series is like an iteration in our program.
So, yes. So you would, in this case, you can just create a little function. So if you were doing Python, if you wanted to go Python immediately, I think, I don't know, you look like you were going to. So basically, then I would create a function that computes f in the neighborhood of 1. Right? Yeah. And then I can actually kind of do test and immediately also spit out what the errors were, so I can actually test it quickly, yeah. So yes, Python would be more effective, but then if you still don't know what the mechanics is of what you're computing, you still need to work it out by hand first. Yes?
Under 3 terms for F2, why don't you subtract 1/3 from 0.375 to find the absolute value?
So here, this is my approximation minus the true value.
Okay.
So absolute value of error is absolute value of the difference between approximation and the error.
Okay, so that's the error.
So typically in errors, we just look at the absolute value. Whether I'm plus or minus doesn't matter, it's just how close am I. And if I was doing relative error, I would take that absolute value and divide it by the actual true value to see sort of the relative size, so I'm only 12% or so, 13% away. So that's not too bad for only 2 terms. Yeah? So again, those are the definitions. Absolute value is true, absolute value of true minus approximation. And my relative error is true value minus approximation divided by the true value. And if I don't have true value, then I possibly have some best approximation to it. So I do the best I can. Sometimes I don't have the number I'm looking for, right? I'm looking for it. That's the whole point of the method. So if I was iterating, then I would just take 2 closest iterations in a for loop to get somewhere, and I would take their difference and divide it by one of them. Okay. All right. Now, what about digital representation of numbers? Okay. So I have a fixed number of digits to actually represent anything on a computer. My storage might seem infinite, and the reason why it seems infinite is that because your music these days is not stored on your computer and or phone, it's actually on the cloud. Cloud being some very large storage computers that Spotify or iTunes or whatever service you might be using for music is using. and just streaming to you on demand. Right? And the only time you actually notice something is like when that tunnel between you and the streaming tunnel between you and the agency that is selling you music or possibly giving it for free might be a little narrow and you don't get things in the best quality, right? But we do have finite storage, so if you had to store all the music yourself, you would have to have sort of a disk that is large enough, right? Now, the way computer interprets things, the only thing the computer knows is on or off. Electricity is on or off, okay? So the only way for us to communicate numbers to a computer is with 2 digits. On, 1, or off, 0. Now humans use 10 digits. Any ideas why? We have 12 fingers, so our base would be 12, but we have 10 fingers, okay? So that's why basically somebody came up with 10 digits. It came from Arabs in whatever century. Yeah. Okay, so they started that system, and that system stuck because it made sense. It was intuitive to all of us because they have 10 fingers, right? So basically, computer goes in zeros and ones, and I'm calling that one binary digit a bit, 0, 1. And we go with groups of 8. Why? 8 is actually a power of 2, so it actually makes sense mathematically. And you just have to give it a finite chunk. So most of the time we're measuring memory in bytes, and that 1 byte is 8 bits. So most of the time you know that your either phone or computer has 8 gigabytes of memory. Okay? That means that it can take 8 times 10 to the 9, roughly, of bytes. So it's 1 billion bytes, 8 billion bytes, that it can keep in memory at one time. If you go over that, your computer will crash. Your memory is finite too. You cannot store more than 1, maybe 2 tests per week in your memory, right? And then your memory starts failing. So when you're studying for a test, you're fitting it all into your sort of current working memory. And that current working memory has all of that information stored, and we know that it deteriorates over time. Okay? Now, a computer will really deteriorate over time if you pull the plug. It does deteriorate over time depending on how many processes are running in the computer at the same time, how many programs. So are we. You're overloaded. If you have 4 tests at a time, that's your memory overload right there. Okay? So we're not that far away from machines in a certain sense. All I'm trying to point out is that there's a certain finite amount of both of what you can currently work with, right? How many tasks you can operate at a time. Computers are the same, essentially. There's limitations in memory. Now, in computers, we can actually seriously quantify things in terms of bytes. In human memory, that's a little difficult to do. So in computers, we can use so-called words, and word will have 1 byte, or it will have 2 bytes, 16 bits, or 3 bytes, 32, that's 4. 4 bytes, 32 bits. Right? So I have to decide for a certain range of numbers that I want to store, what is the size of the word going to be? Okay? So when you're asking computer to fit NumPy, to fit an array into memory, it has to know if your array has numbers 1, 7, and 8. So it has 3 numbers. Okay? It has to know how much memory is it going to use per number to store them. It can use 1 word per number, that's 3 bytes. Or it can go more accurate and use 2 words per number, that's 6 bytes. But I literally have to go to the memory and ask for a chunk of memory to store. Okay? So that's why you need to know what the representation of numbers is and looks like because it's all sort of agreements of how we've over time, since we started using computers, we came to agreements in how are we going to do this. And computer scientists, for the most part, deal with that part and managing it. We need to know the basics in terms of what bites us when we actually program something, right? So we will go through those basics. So I have to first figure out what type of number I have, integer, 3, 7, and 6, whether I'm storing minus or not. That's also an agreement. So I have an assigned number versus unsigned number. I could have real numbers. The foundation for that, as I mentioned, is scientific notation, because I'm going to store this part of the number and exponent separately inside this word that could be, for instance, 32 bits. I have to decide how many bits will go for this and how many bits will go for -7. This is, sorry. I go now, turn it off. And then complex numbers are actually combinations of 2 real numbers. So I gotta double the storage. Right? So it's all kind of, on paper, I'm just writing on paper, and math is easy, but I'm actually now gonna store it in a computer. I need twice more memory for complex numbers than I need for real numbers. And that can cause trouble. All right. So here's exercises. You have only coins of 1 cent, 1 cent and 10 cents. Those are the only coins you have. What is the least number of coins of each kind that you need to have to represent 25 cents? I could go with 25 1 cents. That's a lot of metal. That's not the least number, right?
7.
So 2 of 10 cents.
10 plus 5 of 1 cent.
So we see the relationship between our number representation and that, and the metal in hand. 2 times 10 plus 5 is 25. 2, 5. Our digital system of numbers works by imagining we have ones, tens, hundreds, those are only coins, and reducing the number of metal it takes to represent any number. 179 is 1 times 100 plus 7 times 10 plus 9 times 1. 1025 is 1 times 1000 plus 0 times 100 plus 2 times 10 plus 5 times 1. 1025, yes? That is the foundation of how we represent numbers. So my digits in that world will go, because my basis is 10 and powers of 10, my digits are 0 through 9. If I need digit 10, I'm jumping up in power, right? So you have number 10, that's 1 times 10, which is power of 10. So I don't go with digit 10. My digits are 0 through 9. The moment I get to 10, I'm jumping up in power and adding number of digits that I represent the numbers. Yes? So basically, 25 is the least number of 1s and 10s and any powers of 10 that I get to represent number 25. Does that make sense? So that's the basis of the digital system, of the decimal system that is in base 10. Binary system works the same. It's just working with powers of 2, not 10. And the only digits it has is 0s and 1s. So that's what our computer will do. Okay? So can you do the same exercise? I have now powers of 2, which are 1, 2, 4, and 8 cents. What is the least number of these coins, these imaginary coins, okay, bitcoins? The bitcoin means something completely different. But let's call them bitcoins, okay? So what is the least number of coins in my binary system?
1 of 16.
3.
1 of 16.
1 of 6. So I take the largest that can fit into 25. So 32 is 1 over, so I'm not taking 32s. So 1 of 16, then what's left?
8 and 1 of 1.
1 of 8, and so 3 coins, 1 times 16, 1 times 8, and 1. So basically the way I'm going to represent this number is actually the same. So I'm going to have 1 times 16 plus 1 times 8 plus 0 times 4 plus 0 times 2 plus 0 times, plus 1 times 1. 1, 1, 0, 0, 1 is my binary representation of the same number. And that's what computers can do with on-off switches.
Why did you put the 25 in parentheses with the 2?
Because that's my decimal system. So this is to reinforce the idea, which we actually just take for granted, that we're actually working in decimal system. Now that we're going to switch over, so it's like basically like speaking in English and Croatian. Okay? 10 is English, 2 is Croatian, which most of you don't know, but you're going to learn some of it now. Okay? So basically my 25, it's the same number, it's the same thing that I'm trying to say. It's just when I say it in computer world, I use 11001. I also have to fit this into a 1 byte. So this should have 8 things. And whatever I have above, I'm going to fill in with zeros from the left. Because that essentially means 0 times 32 plus 0 times 64. Right? So basically, I'm just going to add as many zeros plus 0 times 128. Okay? So this is going in where this is power 0 of 2, this is power 1 of 2, this is power 2 of 2, power 3 of 2, and power 4 of 2. The same works in decimal system, we just don't even think about it. That location of 5 is power 0 of 10, which is 1, 5 times 1. Location of 2 is power 1 of 10, which is 2 times power 1 of 10, which is 2 times 10, yes? So as I'm adding this number, basically I'm adding 1 times 1 plus 0 times 2 plus 0 times 4 plus 1 times 8 plus 1 times 16. And that is 25. I can play with this however I want. Computers use binary systems, humans use decimal. Mathematically, we could have base 7, we could have base 14, we would run out of digits. There is base 16 that is used, and then after 10 I start with A, B, C, D. You will see it actually based of 16, there's a direct relationship. It basically just shortens writing of binary numbers. Oh, that's that test. This is the test, and it's about in our classes, and there we go. So essentially the choice of the base is arbitrary, except that in practice we have binary and decimal for the most time.